All right, here we're going to do another improper integral, right? There's an infinity on our limit, which indicates that we have to use the techniques of improper integration. So we're going to make a parameter out of infinity, right? Or we're going to make a parameter for infinity, limit as t goes to infinity. And the basic parameter we use for this one is just t. So hopefully that'll simplify the problem a little bit whenever we plug it in. Now, the hard part here is actually recognizing what this integral is. So we have 1 over something, right? There's square roots. There's a sum. Now, it's helpful to recognize sort of the form of this integral and what kind of substitution we can make. So let's just deal with the integral for now. We're gonna just handle the indefinite. Now, there's no real good u substitution here, right? So if we u sub our bottom, there's no function on top or on the bottom that will give us, right, that'll cancel out with our substitution there. Integration by parts is not really going to work. We only have one function, right? We have the dx here, but that's not going to help us much. I mean, what are the other ways that you could do this? There's no u sub, there's no partial fraction decomposition that's going to be nice, right? Because we have these square roots here, right? If we try to square the bottom, it's not going to help us that much. So we're only really left with two options. We can either give up and go do something more productive with our life, or we can choose the last technique of integration that we've learned, which is, or the last one that, not that we just covered, but the last one that I haven't talked about, which is trying to find a trig sub or recognizing a trig identity. So here, I think it's easiest to recognize where the trig sub might come from. So if we pull out the square root of x, we have integral of 1 over 1 plus x. Right, so this 1 over 1 plus x looks kind of similar to what we might have for right, a tangent, right, or an arctangent, except, right, this x isn't squared. Now, however, right, this x here is the squared of the square root of x. So maybe we can say that 1 over the square root of x, 1 plus the square root of x squared, right? That might get us somewhere. And in fact, if we make the substitution, the square root of x is equal to tangent theta, right? Then we're going to have a tangent here. Then we're going to have x is equal to tangent squared theta, right? And then dx is going to be equal to 2 times tangent theta secant squared theta, right? So if we do that, we're going to get an integral 1 over, right, tangent theta 1 plus tangent theta squared, right, times 2 times tangent theta secant squared theta d theta, and we get something, right? Now it's kind of useful, right? Our tangents are going to cross out. This is going to become a secant squared theta, right? That's going to cross out with this secant squared. So we're just going to have an integral with d theta, and that's actually pretty easy to integrate. We're just going to get theta. So let's go back to our integral that we had up here after evaluating just the integral, right? So the integral we had up here, we had to take it to infinity. So let's take this integral from 1 to t, limit as t goes to infinity, right? And we've already discussed that whenever we do this integral, we're going to get 1 to d theta, right? From this, we're going to get an arctangent, right? Because you're going to get theta, right? And we know that theta, or I guess tangent theta, is equal to the square root of x. So then theta is going to be equal to arctan square root of x. And then don't forget there's a 2 here. There should be a 2. So we should get arctangent of x, arctangent of the square root of x times 2. So that's going to be our answer. Right, 1 to t. Right, and don't forget the limit as t goes to infinity. So expanding it out from our bounds, we get limit as t goes to infinity. We'll pull the 2 out. Arctangent of the square root of t minus arctangent of the square root of 1. And here, so our limit doesn't apply to this one because it'll just be a constant, right? There's not going to be any t to take the limit of. But here we can take, we can impose our limit as t goes to infinity within this arctangent function. So actually, the limit as t goes to infinity of a square root is just going to be infinity. So this is going to be the limit as t goes to infinity, right? Arctangent, right? Square root of t minus arctan. And arctangent of the square root of 1 is going to be pi over 4, right? Because whenever you take the adjacent over, or the opposite over the adjacent, the time when that equals 1 is going to be at pi over 4. So yeah, that's going to be pi over 4. So this one's going to go to infinity, so the limit of arctangent, so as this one goes to infinity, right, goes to infinity, arctangent actually levels off at pi over 2. I forgot the 2's here. So this one, the graph actually looks, it actually asymptotes to pi over 2. Right, it should look something like that. Ooh. All right. Pi over 2. So we have 2, right, and the limit as arctan goes to infinity is pi over 2 minus pi over 4. Right, and so then we just perform some basic arithmetic operations. We get 2 pi over 4 minus pi over 4, which would equal 2 times pi over 4, which would equal pi over 2. So we find that this integral will evaluate to pi over 2, which is actually pretty interesting, right? Our function looked pretty complicated in the beginning. We were able to figure out that there's not going to be a good u substitution. There's not going to be good partial fraction decomposition. There's not going to be a good integration by parts. So we had to figure out some trig way to do this, and that was the best way. This one takes a little bit to recognize at first. But once you do find it, the integral actually becomes pretty easy because our tangents and our secant squareds will cancel out, and then we'll get some things in terms of pi, and you'll get the correct integration. So this is actually a pretty cool integral.